Okay, so today's announcements, there are fewer. I wish there was one more, but it's not quite ready. So homework 1 is due on Friday. Lab sections meet this week, and there's a programming assignment that's not quite ready to go out yet, but it's really, really close. I was working on it to get it out before class, but it didn't work. Today's plan is to go over correctness, but before we do that, there's a warm-up question, which is completely unrelated to anything at all. Really, I mean, but do you know what the answer is to this question? If you start playing tic-tac-toe and the first player, do you remember tic-tac-toe? Tic-tac-toe, you have to get 3 in a row. It can be either a diagonal, a vertical, or a horizontal, 3 in a row. And there are 2 players. One's the X player, one's the O player. First player, X player, played up in that corner. The O player played in the other corner. Who wins? Now it goes back and forth between the first and second players. Are we assuming that they're rational? You mean intelligent? Well, I guess you could make that assumption. But even if you're rational, you could be wrong. I mean, you could make one. Yeah. It depends on what moves they make, but I see the first person winning. If you put 2 incredibly intelligent people into this game and told intelligent person 1 to be the first player and intelligent person 2 to be the second player, who would win in that case? Like, I was in this position with my daughter, who was like 8 at the time, and I actually won still, but that wouldn't happen anymore. Yeah.
X had the strategy to guarantee you win, but if you don't play to that strategy, then all bets are off.
Yeah. So X has what's X's strategy to play to a win? What's the first move for X at this point? X has a player. What's the first move? No? Pick a corner. Any corner? Okay, good. Pick a corner. Any corner. Yeah.
I thought it was pick a corner the opposite.
Isn't this interesting? This is like an algorithm, right? But it's a 2-player algorithm. It's between 2 things, both of them intelligent, both trying to win. It's a game. There's a lot of work done in computer science on algorithmic game theory. This is one of the simplest games that are analyzed that way. If you start with no play, the board is empty. It's for 2 people that are playing optimally against each other, it turns out to be a tie every single time. That's why you never play tic-tac-toe anymore, and that's why I have to remind you about what tic-tac-toe is, because it's only fun when you're not playing optimally. So anyway, this is an example where if you don't play optimally as the second player, the O player, you can get yourself into a bad situation. So it is true that if you play in any corner as the X player, you will win if you play logically. Isn't that fun? Okay, as I said, this has nothing to do with today's lecture at all, except to get your brain going and thinking about stuff. And the stuff that we're thinking about today are loop invariants, which are not tic-tac-toe, but they're almost as much fun. So the loop invariant that we were trying to prove for this code, which is called findmin, findmin is this piece of code that I've scrunched up into 5 lines by cleverly not putting carriage returns after the semicolons on several lines, but it's the same code as last time. So it starts off by picking up the first element, the element in location B, and then it looks from B onward for something that might be smaller, and if it finds something, it swaps it with its current guess as to what the smallest is. So it eventually gets to the end, and it, according to our claim here, it will find the minimum in the rest of the array, b through n, or b through n minus 1. Okay, so that's the code. That's what it does. It marches down and keeps track of the minimum as it's going. The loop invariant that we have stated here is something that's true someplace in here, someplace in this first line of the for loop. The invariant holds true. So then when I say I have a loop invariant, it's important to understand where that invariant is true, and typically you choose it to be, well, you can typically choose it to be at the top of the loop. You can choose it to be wherever you'd like, but for this particular example, it's good to have it at the top of the loop because it turns out that's a nice thing to work with for this one. And by nice, I mean it's easy to prove, and proving it gives you the result that you want, that the code is correct. Okay, so let's go through this proof. We talked about last time what the style would be, what the approach would be to proving this, and there were a couple of options, contradiction and induction, and I'm going to use induction. And induction is great for loop invariants because it essentially is an inductive process. This loop is trying to modify a state over time incrementally, which is essentially what a proof by induction is doing. You're taking an inductive step at every part of an inductive proof. And we'll see that this is going to mimic, basically, this proof is going to mimic the code almost exactly. So, okay, great. So how do we start? We're going to start by saying this is going to be a proof by induction. By induction on what? For loops, you are trying to make a statement about each contribution of the loop iterations to the preservation of a statement. So induction is always driven by the number of iterations through the loop. Now, to make our lives easier and to make the proof readable, we won't introduce a new variable which says how many times I've gone through the loop. We'll just use the loop variable. So we'll do induction on I. You see, I doesn't start at 0 or something like that. It starts at b plus 1. That's okay. We can deal with that. Induction doesn't have to start at 0. Everybody okay with this? You could choose whatever you'd like. You could make up a new variable, call it k, for the number of times through the loop, and you would say k is equal to 0 before you actually execute the loop, and it would be incremented each time it goes through. It's perfectly fine. But it's sort of simpler to write things when you just use I, because I is like an index that gets used a lot. Okay, now what's the first thing you do when you're trying to prove something by induction? Well, actually, there's something before that, really. The first thing you do before you do that is you actually, this is even before you start writing down a proof. The first thing you do is you believe what you're trying to prove. So, I know this sounds stupid, right? Why would I ever start trying to prove something I don't believe? Believe me, when you do your homework, you're going to sit down and start writing out a proof before you even know what you're writing. I mean, it happens all the time, and you can see it when you read it because it's sort of, there's a meandering narrative going on in the proof. And anyway, I know you won't do that, but I've seen it before. So before you do it, you first have to believe it. That's why we did that sort of proof by words last time. That sort of argument that said, this is what's going on. It seems to be keeping track of the minimum so far. And it seems to be maintaining that as so far increases. That goes farther and farther down the array. So, okay, so number one, you got to believe what you're trying to prove. Then we chose the way we're proving it is by induction, and then you're right. You're absolutely right. The next thing to do is base case. In our case, in this case, the base case is when I is its initial value, which is b plus 1. And when I is equal to b plus 1, this is at the top of the for loop. This is before the body of the for loop has executed. What do we know at this point? Well, we know that R and S have already been set. They've been set to the bth element of array A, that's S, and R has been set to B. So I want to write down IE before the loop executes. And so at this point, we want to verify a loop invariant is true at that point. S is in fact A of R. S is the string that's in A of R. That's true. And it's the minimum of A, B through I minus 1. I minus 1 here is B plus 1 minus 1, which is just B. So it's true that, I'm pointing at there. Let me point up there. You see AB? S equals AB. When I is equal to B plus 1, S is still AB. And AB is the only element in A, B through I minus 1. By the way, somebody asked me last time, and I didn't tell anybody about this, so let me tell you right now. Those dots there, what do you think those mean?
B through I.
B through I. B, B plus 1, B plus 2, B plus 3, all the way up to I minus 1. Okay? It's not through I, it's through I minus 1. B plus 1, I minus 1. Okay. So we're okay with the base case. The base case is true. Because there's really not very much to prove. That's the only thing we have to show, is that A of B is what S is, and B is value R at this point. Okay, now what do we do? It's like a recipe in proof by induction. It's almost like you don't have to engage your brain at all. Not true. But anyway, what's the next step? You write down your inductive hypothesis. Your inductive hypothesis is that the statement is true up to some point, up to some iteration I. That's what you write. So you'll say, assume at the start of iteration I, that's some iteration, that we know that S, which is A of R, that's a bracket, is what we claimed it to be. It's the min value in what we've seen up till now, which is B I minus 1. That's just restating our loop invariant. It's restating it as the assumption that we're going to make prior to increasing I, going to the next step. Now, going to the next step part is the inductive step. And the inductive step says what happens when we go through the loop one more time. Is it true that after we execute the next iteration of the loop, that this is going to remain true for the next value of I? Is it going to work? It's going to work. Why is it going to work? What's going to happen? Yeah.
Well, just for clarification, so for the base case, when I equals B plus 1, like, what are we showing that is true in that scenario?
The loop invariant. This whole proof is to prove the loop invariant is true. And this,
And it's true because S is equal to AB at the time.
S is equal to AB and R is equal to B.
But since the loop has an executor, so AB has to be the smallest.
Because I is equal to B plus 1,
Yeah.
the only element that's being considered is AB. So, because we're saying that something here is the minimum of something here. And this something here that I circled is now just one thing. And that one thing happens to be the same thing as S. So there's nothing to prove, really. I mean, it just is, there's only one thing, and that's the minimum.
Oh.
Yeah.
Can you explain what's an invariant again?
It means that it's something, it's just a statement. And a statement is true over some loop, usually, or sequence of statements, usually. In this case, it's true for all I from B plus 1 to n. And so it's an invariant because it holds without variation over all of those iterations from I equals B plus 1 up to n. Yep.
Why don't we also include that like R is true in the loop?
R is true?
Like it's the right index.
We did. That's what that equality sign is saying. This is my sneaky way of saying that R is the right thing.
Oh, okay.
S is the thing the string that we're talking about, and its index in the array is index R. And I cleverly put that into 3 symbols.
So you combine both.
Yeah, you can write it out if you want to, but I don't have very much space, especially considering the way I write. So, yep.
I was going to answer your original question. What happens to that plus 1?
Oh, great.
There's 2 cases. One is that an index I plus 1 at the minimum. What does it become?
Great. And then it just follows from that. Perfect. Let's move on. No, we have to finish this. By the way, all of this, if you're vigorously writing this down, there's actually, I wrote the proof down already. It's on the website. It's called Proof. And you just click on it and it shows you the proof. So you don't have to write anything, and you could go to sleep for a while, but this is the only proof that I've written down for loop invariance. So anyway, it's good to see a loop invariant proof expanded out, but we're going to do it here too. Okay, so what happens in the inductive step is we have to look at the code, because the code's what's going to be happening during that step, and we have to understand how it changes the state. And he's exactly right. There's 2 possibilities. During the body of this loop, which is this line here, either that if is true or it's not true. So if it is true, if AI is less than S, then we actually change the value of R and S. And if it's not true, then we don't. This makes perfect sense, because what we're trying to do is have R and S track the smallest value. And this is saying if you found something smaller, you better change R and S so they track something new. So what I wrote down here, what did I write down here? Oh yeah. I got tired of writing down iterations, so I just write iter. During iter I, we compare, can you read that? How many people cannot read that? How many people can? I don't know how to ask this. Anybody upset? You're upset you can't read it? Really? You know, you're right. I can't even read it. Let's compare. I will write bigger. Is that big enough? I see, it's just this fine. Okay, fine line. Okay, during iteration I, we compare something against something. We compare S to AI But notice that S is something that we have a truth about. We know that S, by the inductive hypothesis, is the minimum of what we've seen up until the step before step I. So S is the minimum S is the is AR, which is the minimum of A, B through I minus 1. And what we're doing is comparing that minimum against AI. So this is by the inductive hypothesis. We're comparing it against A sub I, and if it's true, if S is smaller, I'm sorry, if AI is smaller, if AI is smaller, we update. And we replace R with I and S with AI. And so if it's not, then we don't do the update. So at the end of this process, oh, that's an at. At the end of iteration I, we have the answer. We know that A, R is the minimum of the minimum of A, B through I minus 1 and AI. And the minimum of the minimum in that array and AI is actually just the minimum over everything. And so then we go on. So we go to the start of loop I plus 1. I got to tell you, we're not going to do many of these proofs in class, that's for sure, because I'll get writer's credit. But do it once or twice. You have any questions about this? Now, updated, yeah.
Do we have to state explicitly, like, if A sub AI is not less than S, then it's S is still the same?
We sort of did that, but in a sneaky way. Look, this is not there's not some, okay, I guess you're coming out of 121 where there's kind of like the magical formula that you have to write down for it to be a proof. You've just gone to 221. There is now not one magical formula that you will write down for a proof necessarily, especially when you're proving loop invariance, where I'm telling you you can choose the variables that you're using, you can choose the way that you're going to break down the thing by induction, you can choose all of that yourself. What we're really getting at in this proof is an explanation as to why it's true. And everybody that takes this class hates this part of the class. This is the part of the class where I tell you there is no foundation on which to build your proofs like there is with geometry, for example. Remember proving stuff using Euclid stuff? This is all about understanding correctness of code. There's some rigor in what I'm writing here. There's some notion that I have to make claims that are held to be true as I go through this loop. But those statements are made in sentences. And it's not like I'm writing down a formula there. I'm writing down a sentence to explain something to you. So this is the bad part about these proofs, is that there's no like one answer that you can just find. There are many ways to prove it. And the other thing is that you have to be sensitive to your audience. So the proof that you write for another computer scientist or the proof that you write for your boss is different than the proof that you would write for somebody without that background. They wouldn't understand what we were talking about when I wrote down min of a through b of I minus 1 to ai. They would be like, what? Why is that equal to the min of a through b? I mean, what? You have to be sensitive to the audience as well in proofs. So I understand that, and I appreciate the fact that it's now like you're gone off to sea without a paddle, but that's the way proofs are in this class. No, they're not. They're like something else other than a boat without a paddle, but they are not the same as a formula that you write down. They're words. Okay, that rant is now over. Any other questions about this? Are we done? Well, we're done proving a loop invariant, but we haven't proved the correctness of the code. So let's just hold on for a second and see what we still have to do in a bit. But before we do, I wanted to talk about this loop invariant proof. This is sort of a general scheme. When you do a loop invariant, you want the invariant to be based on induction variable that goes over the number of times that you take the loop. Sometimes that's the number of times you go through the loop. Sometimes it's just the index of the loop. Then the base case, you prove it before the loop starts. Typically, you could, sometimes you might prove it at the end of the loop, but that's hardly ever the case. You have an inductive hypothesis. You have an inductive step. And then this is the part that we haven't done yet. It's the extra bit. So the extra bit is you've got to use the loop invariant that you've proved in order to show that the correctness of the algorithm follows. In our example, we have, is it okay if I go backwards? In our example, we have this interesting statement that the loop invariant is true for all I ranging from b plus 1 to n. This was also mentioned last time. People had questions about this. Why is it going up to n? I actually is never an index in this loop that's at n. It's always stopped, right? It's got to be less than n. But this invariant is an invariant that holds at the beginning of this loop, so up here. And so at the beginning of when I reached iteration, let's say I reached iteration n minus 1, I would go through that loop, I would come back up to the top, I would increment I by 1, I would then be n, my loop invariant would be true for I equals n, and I would go into this loop and immediately fall out because I is now n, and so it's no longer less than size. And so the top of the loop is the place where the code exits out of the loop. And if I have that invariant being true for all values of I up until n, then when I come out of that loop, I know that my invariant holds, for example, when I is equal to n at the bottom of the loop. Okay? Think about it a little bit. You got a variable that's incrementing one more than it should before it drops out of the loop. And yet we're proving an invariant. If it's true at step I, it's true at step I plus 1 for all values of I up to n minus 1. So, okay. So we've done that, which means that we have this invariant. We have this invariant true for I equals n. when I equals n, this range is the entire array from b to n minus 1. And what that means is that the find min code will find the minimum value in the entire array starting at location b all the way up until the end of the array. Oh yeah, there was another question I forgot to mention as well, so let me mention it now. What is n? N is the size. If you didn't have that piece of information up until this point and you're confused, maybe that will solve the whole thing. Anybody have any other questions about this proof? So now we've fallen out of the loop. I is at n. We have the correctness from the algorithm that follows from the truth of the loop invariant. That's the extra little bit at the end of a correctness proof. Then the last sentence on this slide is maybe the most important, which is, I know this seemed like a really maybe slow, tedious process of trying to understand one simple piece of code. But when you're designing an algorithm to solve a problem, you need to break that solution down typically into loops or recursion or something which processes things incrementally, and understanding what you're trying to do at each step of that iteration, that's crucial for making sure your code is correct. So understanding how the state of the system, the state of the computer evolves increment by increment, loop by step of the loop by step of the loop, that's critical to making sure your code is correct. And that's the best reason to think about loop invariance. It's not to try to prove what you've written is correct. It's to try to think about what you're doing to make sure what you're writing is correct. Any question about this? Yeah.
So I just wanted to confirm to prove the extra bit, we just consider the last case, when I is equal to n.
For this particular piece of code, yeah. So we didn't have any post-processing after that. After the loop fell out, there's no other line except to return R. So what we had to show was that R was the right thing. And that's coming directly from the loop invariant at I equals n, at iteration I equals n. That's all we had to do. Now there may be post-processing. For other algorithms, you have to do some more work, and then you'd have to include that into the proof of correctness if it was needed to prove something that you wanted to prove was correct.
How do you know the invariant is true for I equals n?
Because I know that I proved that for all values of I less than or equal to n minus 1, which I never actually stated. But for any value such as that, we can go through this inductive step.
But the loop doesn't include n.
Pardon me?
The loop doesn't include n.
That's correct. So there is this whole discussion about when I start a loop at n minus 1, when I is equal to n minus 1, it iterates the loop. And then when it gets to the bottom, what does it do? I goes up to the top, and it becomes n when it comes up to the top. It gets incremented. And then at that point, you're at the top of the loop for the iteration of I equals n.
Yeah.
And what happens? It doesn't execute the loop, but it does the test, and then it bails out. And so I could not prove the inductive step from going from I equals n to I equals n plus 1, because nothing happens, and that would be distressing. But for I equals n minus 1 to I equals n, I can. Something happens, and it comes back to the top of the loop, and it falls out. And if you were actually not using C++, but you're using good old C without the int declaration within the for, the value of I would actually be n at the end of that loop. Because it does the increment, and then it tests, and then it falls out. Any other questions about this? Okay. Yay, you now know loop invariance. What does this do? This is using something that you know. We just proved the correctness of that code, finding. But this is taking a vector of strings and it's looping through that vector. What's it doing? Yeah. It sorts it. Yeah, it sorts the vector A. It sorts the vector of strings. How does it do it? What policy is it doing? It looks for the min, and then it swaps it to the front. Oh, by the way, swap means swap A for B. Swap AI for A min. So there's two elements in the array, you swap the two. By the way, you probably could write, can you write this? Can you write this in C++, the general swap routine? How would you pass the parameters into your generalized swap routine? By reference, because you want the swap to actually occur in the caller's frame. So if I call swap here, you know what the signature is for swap. You know it says swap ampersand, no, it says swap string ampersand A, comma, string ampersand B. That's going to be the signature for that function declaration. And that's saying that those are reference parameters that are being passed, so the swap will perform it. And then it'll do the normal thing. It'll go put this in a temp, move that over there, move it in there. You know how to swap stuff. Do you know how to swap stuff? Okay, good. All right. So it sorts. It finds the minimum in initially the entire array, and it swaps it to the front. And it finds the minimum in what remains, and it swaps it to the front. This is repeated until the end. This is a sorting routine that is called selection sort, because it's selecting the minimum and putting it in place. Selecting the minimum, the next minimum, putting it in place. The selection sort. What's the runtime? Yeah.
Also, in this case, is the swap moving the minimum value, the current minimum value, to like towards the end of the list?
No, all it's doing is it's moving A min into the location AI.
AI is presumably getting further right down.
So is A min. Because min is always greater than or equal to I, right? Because the index that's returned by find min, you know, is always greater than or equal to I, because it's only finding the minimum among I through n minus 1. Okay, so what's the runtime? Way in the back.
O(n) squared.
Order n squared. Great, done. Everybody good with that? How many people are not good with that? Remember what the running time of find min was? Find min, we talked about it as being a single parameter function. When we did, we said its running time was order n. Really, its running time is dependent on the amount of time it takes to compare strings and all of this other stuff, but we didn't actually care about that. But at one point we did, but maybe now we don't. Anyway, if you wanted to compare long strings, strings that are of length n, then n would be another parameter that would have to be put in here for, so with this step, this find min step could actually take order n squared if you counted the cost of doing the comparison. But I'm not going to do that because everybody will be happier. So this is with a constant time compare. And if this takes order n, and there's a loop that's looping over this work that's being done, that's taking order n to find the min, and the swap is constant. The swap is done by indexing into an array, which is constant time, as long as the array is not too big. And so this is order 1, big O of 1. And so you're right. There's n iterations of this loop. The work done in each iteration is order n. So the thing is order n squared. Big O of n squared. It's less than or equal to some constant times n squared. Under my assumption. Is this a tight bound? Is this an asymptotically tight bound? Meaning, is the runtime theta of n squared? In the worst case, remember, we have to be talking about running time in some quantification, like max. That would be the worst case that this thing could do over all inputs of size n. Is it theta of n squared? Well, you know that actually this find min doesn't take time n, it takes time n minus I, because that's the only amount of time that it has to work. So really what this is it's the runtime is the sum of n minus I over all values of I. Something like that. Something like that. What is this sum? Well, it's the same as the sum from 1 to n. What's the sum from 1 to n? Exactly. This is something like n times n plus 1 over 2. So it's about half the size of n squared. So is this theta of n squared? Sure, because constants don't matter, right? The definition of big omega says that, which is what we have to show. We know it's big O of n squared. What we have to show is big omega of n squared. And big omega says, is there a constant such that for all values of n sufficiently large, bigger than some n0, that the running time is greater than or equal to that constant times n squared. And in this case, you could pick that constant to be a half. And you'd be all set. Okay? So yeah, it's theta of n squared. All right. Next, loop invariant. What did I write down as a loop invariant? Holy cow. That doesn't look like a good loop invariant. What is the loop invariant? There's a loop. There's only one loop. So you know what the invariant is going to be looping over. What's happening? How is it making progress towards the ultimate success? Yeah.
At every I, the list up to I is sorted.
At every I, the list up to I is sorted. A0 through I is sorted. Is that good enough? Is that good enough for you? I mean, you got to think about the inductive step now. You got to think, okay, what's going to happen next is that I know that the first A0 through AI is sorted. Now what's going to happen is I'm going to look in the rest of the thing. I'm going to find the minimum. I'm going to move it up to here and plop it down, the minimum in what remains in the array. I'm going to pick it up and I'm going to put it at the end. And now I have to claim that A up to that extra thing is sorted. So there's one part of that which is easy. There's one part of that which is good, is that we found the minimum of everything that remains. So we know that the thing we're moving here, the thing we pick up, which is min, its string value is less than or equal to everything that follows. That's good. Do we know that its string value is greater than or equal to everything that's already in there? Is that part of your invariant? Well, it's true that what's in this range is less than or equal to this thing that I've picked up and plunked down at this position. It's true. But the loop invariant has to be strong enough to say that, because we're going to, when we prove this, only use that loop invariant. We want to put enough muscle into the loop invariant so that it can prove that at the end we're getting something that's sorted. And when I have this loop invariant, it's not enough. Because it could be that A0 through 1 is 0 through I is sorted, but it could be like, for example, all the big elements in the array, all sorted at the beginning to satisfy this loop invariant. You don't have enough in this loop invariant to sort of say precisely what is achieved by the first I iterations. So the loop invariant that you've said is correct, but it's just not, it's not strong enough. It needs to be a little stronger. Yeah.
You also need to mention that the very first element of the sorted distance depends on the remaining element. So it is always going to be, the first one is always going to be smaller than the next one.
So in fact, all of them are this small. So this is sorted, and they're smaller than anything that remains.
Within the sorted list, it is also like from minimum to max.
Oh, no, that's saying this is sorted. That's definitely true. So A0 through AI is sorted. This is what was said before, but there's the additional fact is that all of the elements in this part of the array, I'll write it down, and A0 through I is less than, or equal to, I suppose, AI plus 1 through n minus 1. That's what you're trying to say, right? Yeah. It's sorted, and they're all less. They're all small. Is that good enough? Yeah, well, there's another nitpicky thing. Yeah.
Do you say that it is sorted at the end?
Say it again.
Do you say that it is sorted at the end? Because you say that.
Oh, no, I have to prove that it's sorted at the end of the loop. That's the loop invariant is the part.
At the end of the equation.
Oh yeah, I have to tell you when this is true. Yeah, that's a good point. I haven't gotten to the quantification yet. You're absolutely correct. I've got 1 minute to get there, so I'm going to get there. But is this good enough? Everybody happy with this? There's one other nitpicky thing that you can argue about, which is that it could be that somehow this code changes the contents of the array A. So why are we doing a swap? Because we don't want to change the contents of the array A. So we have to put in something like it's the same as the original input, something like that. So let's say it's sorted, and the set, or multi-set, if you care to put that down, and the set of strings in A remains the same. And this is a loop invariant that should be true for all values of I from 0 to n. And it should be true here at the start of the loop. For all I from 0 to n minus 1, no, n. Okay. Oh, I have 2 minutes. That's excellent. My watch is wrong. Any questions about this? This is the loop invariant for selection sort. The loop invariant for selection sort is so drop dead easy to prove that I'm not going to prove it. We'll move on to the next thing, which is insertion sort, and we're going to move on to that just to show it to you. This is part of insertion sort. This is a subroutine in insertion sort, and I will tell you what the name of this mystery function is. What did I call it? I called it put in place. And your task before Friday is to, without cheating, figure out how you would use put in place to sort. And then you'll have invented insertion sort. And then you'll be famous. I will see you Friday.